We're going to go on to talk about physiological measurements in a moment, that is measurements from a human subject. But before we do, I just want to illustrate one of the particular problems we're going to face. So the signals we're going to be trying to measure are in the region of 100 microvolts, which is 100 millionths of a volt, to maybe 1 to 5 millivolts, which is somewhere between 1,000th and 5,000ths of a volt. So those are small signals typically created by cells in the human body. Now, what I've done here is to replace the signal generator that we were just using with this lead. So there's nothing else between this lead and our oscilloscope and our loudspeakers. Nothing at all. It's just a piece of electrical cable. So I'd like you to watch what happens when I touch the end of it. So I think you'll immediately see and hear that we have a lot of interference noise. And although you won't be able to read the oscilloscope screen from here, I can tell you that that's round about 100 millivolts in amplitude. So that's maybe somewhere between 100 and 1,000 times bigger than the signal we are trying to measure from the human. You might wonder, where does that come from? And I suspect some of you will have an idea. Anybody who's tried to plug a stereo in or a musical instrument will have heard something like this. You'll get a clue if I do this little experiment. So I'm going to touch the tip like this, and then I'm just going to get hold of this electrical mains cable around the back of the instrument here. And you'll see that when I hold onto the cable, the amplitude of the noise gets substantially bigger. And that's because that noise is created just by my body picking up mains interference from all the electrical wiring that's around me. So of course, if I hold onto a mains cable, then the noise gets bigger. So there are things we can do, move people away from mains cables, but the fundamental problem is the mains interference on my body is always going to be much, much bigger than the signals I'm trying to measure. How then are we going to solve this problem of recovering a tiny, tiny physiological signal from among all of this noise that's all around us? Well, this instrument on the desk here that we'll be looking at in a moment is an amplifier. It's not so different to the amplifier that you might have in your stereo at home, but there are a couple of really important differences that we'll come to talk about. So the similarities, first of all, the amplifier makes a small signal bigger. Well, you can see how that's going to be helpful because we're after recording a small signal, and so if we can make it bigger somehow with an amplifier, then that's going to help us. The problem is, though, that an amplifier makes everything bigger, so of course it will make the signal bigger, but it's also going to make the noise bigger as well. And so an important number that we tend to talk about, the signal to noise ratio, doesn't get any better. In fact, it might get a little bit worse because the amplifier will add a little bit of noise itself. So there are two important differences between this amplifier and the one that's in your stereo at home. First of all, there's an issue of safety. On the back of an instrument like this, particularly if you buy one these days, you'll find a CE mark. The CE mark essentially says that it's safe. And what that means in the context of an amplifier is that by connecting it to a patient, you're not going to do them any harm. You might wonder how an amplifier could do them harm. Well, hopefully it wouldn't. And in fact, in most cases, you could connect yourself to your stereo at home and you wouldn't have any ill effects. The problem isn't so much this amplifier, but it's what else the patient might come into contact with and whether the amplifier in connection with that other piece of equipment might cause a problem. So for example, if you were to be touching your stereo amplifier at home and inadvertently, with your other hand, you were to touch a live light socket for the sake of argument, you would get a shock because the electrical current would flow from the light socket through your body, across your chest, which is incredibly dangerous, through your amplifier and down to earth. Well, in most cases, you'll be able to avoid that at home, and probably you'll let go of something pretty quickly. Occasionally people are electrocuted in that way, but it's rare. If you're actually wired to the instrument and you're unconscious in a hospital bed, an ECG machine for the sake of argument, that's a really risky situation. In an amplifier designed to be connected to patients, we divide the amplifier into two parts. The first part, which is connected to the patient, the second part, which is connected to the rest of the world. There's an air gap between the first and the second parts, big enough that an electrical signal can't get from the patient to the rest of the world. The signal itself gets across the air gap by some other means, and very often that's done optically. This arrangement is known as electrical isolation.